All right, so we'll continue on now with another concept that we can use to help us determine the delta H for reactions. And we're going to introduce a term here called the standard enthalpy of formation, which is abbreviated delta H, like this a little bit bigger, delta H with a little degree sign at the top, and then subscript F, right? So this means the delta H, we know what that is. That's enthalpy change in enthalpy. F here, the subscript F means formation. And then the degree sign, that means standard condition. So what exactly, first of all, does this mean? And so the formation, right, is defined, is when one mole of that thing forms, first of all, whatever that thing happens to be, and then standard conditions are the conditions under which that process needs to happen. So those conditions are different, whether we're dealing with gases. So for gases, we're looking at a particular pressure at 1 atmosphere. For solutions, the standard condition is 1 molar concentration for solutions. All right. So the standard enthalpy then of formation, again, is the heat change that results when 1 mole of a compound is formed from its elements in their standard states. All right, so for instance here, this equation represents the delta H of formation for CO2. Right? So this here would be the delta H formation for carbon dioxide. So CO2 is made up of carbon and it's made up of oxygen, right? Those are the elements in their standard states that we find in CO2. And when you have an element in its most stable form, so for example, carbon in the form of graphite, the delta H of formation of an element in its most stable form is always 0. So this will similarly for the others as well, we would see that for elements in the most stable form, the delta H of formation is going to be 0. There's an exhaustive list of the delta H of formation for lots of substances. They are in appendix 2 of the textbook. We can use those to help us determine the formation, the delta H of formation of lots of different things if they're very difficult to actually measure in the lab. So let's take a look at an example. We define, again, the standard enthalpy for reaction. We talked about the standard enthalpy of formation, first of all. The standard enthalpy for reaction we define as the enthalpy of a reaction carried out under standard conditions. Okay, and this here again would have the delta H with a little degree sign on, right? That always means, when we talk about reaction, these means standard conditions and then products, and they would be for that particular reaction. So if we have a general equation where we have, A plus B reacting to form C plus D, then the way that we use the standard enthalpy of formation to determine, so here we're looking at using delta H of formation to calculate the delta H of standard enthalpy for the reaction, is the same thing that we've been doing all along. We're looking at delta H for the reaction. It would be products, final minus initial. Okay, and in a reaction, again, the final things are the product. Those are the things that we end up with. Then the initial things are the reactants. Those are the things that we start with. And then now we're looking at the delta H of formation for the products minus the delta H of formation for the reactants. And now if we have more than one, we have the reactants, we need to sum those. So this abbreviation here, that's the symbol sigma. Okay, that means sum of the delta H of formation for the products minus the sum of the delta H formation for the reactants. And we also need to consider stoichiometry, specifically the stoichiometric coefficients in the reaction. So these get multiplied by the delta H's of formation for each reactant or product. Okay, so that's what this long and complicated looking equation looks like. That in essence is what it's saying. Okay, we're still relating final to initial. In this case, it's the products minus the reactants. We're just going to look up these delta H of formation values in our appendix and stick them into this equation. All right, so it says here, using data from appendix 2, calculate delta H for the reaction of AG. Let's write that out. We have AG plus AQ plus Cl minus AQ to produce silver chloride. Let me use a different page. Okay, so Ag plus Cl minus to give AgCl solid. All right, so what we need to do then, in order to calculate this, in order to calculate delta H standard for the reaction, we're going to take the delta H of formation for the products, which in this case is the AgCl, and then we're going to subtract the delta H formation for all of the reactants, which in this case is the Ag plus and the Cl minus. All right, so we need to look up the delta H of formation values from the respective table. And again, you don't need to memorize the values. If you need them, you'll get them. You'll be provided with it, a list of them, or you can look them up on your own. So we can find those in our table. So then we have our delta H for the reaction. So for the delta H for formation of AgCl, so you look that up, that is negative 127.0 kilojoules per mole. For the Cl minus, that is negative 167.2. And for the Ag plus, that is negative 127.0. So when I stick this in, right, their products goes first. So that is negative 127.0 for the AgCl. And then we're going to subtract now, put all of this in and separate it from the rest of it. So we have the Ag plus and the Cl minus. So that is negative 127.0 plus negative, oops, I think I misread. The Ag plus is plus 105.9, my apologies. Ag plus which is actually a good example of where it's very easy to lose track of your signs. This is plus 105.9. Close parentheses, so that gives negative 127.0. Okay, then we have, this is going to be minus, if we add these together, so we have negative 127.0 plus 105.9, negative 127.0. What does that give? Here's minus negative. Did I put the wrong number in? Did I? Yes, I did. Again, very easy to reach out. Negative 167. Oh. Okay, so that made 167 plus 105, that should give me negative 1.3, I think. Yes. And then that would Evaluate this, negative 1.7 plus now 61.3, and that's going to give me about negative 65.7 kilojoules per mole as the delta H standard for that particular reaction. As I was going through that process, you probably saw different instances where it's very easy to make mistakes. Number one, keep track of the numbers that you look up in your appendix, and you put them for the correct values. That was a mistake that I made when I went through. And the second, probably the more common source of error in questions like these, is keeping track of the sign. Okay, so you have all sorts of signs to pay attention to. That is probably the most common source of error in problems like these, because you have negatives and positives all over the place. You want to make sure that you keep track of those when you do questions that involve looking up these values. Okay, let's take a look at another one. I'm not going to go through this one in a whole lot of detail. I just want to sort of touch on maybe the first couple of things in terms of how you approach questions like these. Because this will involve using Hess's law, as we talked about before. So it says, given the following information, calculate the standard enthalpy of formation of acetylene from its constituent elements. So we're given all of these. And what we need to find to calculate is the standard enthalpy of formation for acetylene, which is C2H2. Okay, and if you try to look this up on your table in your appendix, you're not going to find it, right? So it's not like, oh, I can just go look it up in the back of the book. No, it's not in the table. We need to calculate it. So what we need to do is to actually determine what equation or what process represents the formation of acetylene C2H2. So we want, and again, the way that we define the standard enthalpy of formation is the formation of 1 mole of that thing. Okay, so it needs to be one of this from its constituent elements in their standard state. So what is acetylene made up of? It's made up of carbon and it's made up of hydrogen, right? And hydrogen in its standard state exists as H2. It's a diatomic molecule. Carbon in its standard state, right? You'll see when you look it up in your textbook, you'll see carbon. You have a choice of either graphite or diamond. Well, graphite is the more stable because it has a delta H of formation of 0. So we're going to choose that one. The carbon for graphite here is what we have, right? So we have the basic equation written for the formation of acetylene, 1 mole of acetylene, right? So this number here has to be 1, which means we need to go and balance our equation now to make sure that we have, guess what? 2 H's on the right, we have 2 H's on the left. We have 2 carbons on the right, now we need to have 2 carbons on the left, so we need to put that 2 in front there to balance it. So in equations or questions like these, you actually need to determine, you need to come up with this equation. With a delta H of formation equation, and that is your target equation in this problem. And once you know what the target equation is, right, what we can do is the same thing you did with the Hess's law example back before. We can apply Hess's law. Okay, so you need to come over this delta H equation, target equation, then we're going to use Hess's law to solve. All right, so that means we're going to manipulate these. We're going to move them around to get them in the right place. We're going to multiply or divide, reverse equations. Don't forget, if you do any of those things, you also need to affect your delta H values. Then we add them up to get to the target equation that we came up with at the very beginning.